All right. Well, thanks for having me. As Suresh mentioned, this is somewhat a summary talk of a lot of different work that's been done with Gemini over the course of effectively my entire astrophysics research career. And so I realized I entitled it a decade, and I forgot how old I was, and it's actually a lot more than that now. That'll become clear. And so all this stuff that I'm talking about is done as a part of the Sloan Giant Arcs collaboration. So this is kind of a current census of the people involved. The folks colored up in kind of orangish brown here. That's my group at Cincinnati who were all presenting work at the meeting. So hopefully you enjoyed what they had to present. But we're a pretty small group, pretty tight knit. And we've been doing a lot of work over the years. It's all built around this idea of finding bright, strong lensing clusters in the available shallow ground-based imaging. So it started with things like SDSS and RCS2, and nowadays it's evolving into things like decals and DELV. And an interesting thing to note here is that we're looking for really bright giant arcs. And so we're actually pretty close to the point where we found them all, because a really substantial fraction of the sky has now been imaged in the optical and multi-band surveys to depths comparable to Sloan or typically deeper. And well, the regions that are outstanding are often very sort of galactic focused, and it's really hard to find extragalactic stuff out there anyway. So we're coming close to a census of what we'd really call all of the brightest giant arcs that are in the observable universe. And it's a pretty good sample to work with for a couple of reasons. I want to first emphasize what I'm talking about when I mention bright. So I've picked out two things here. These are two of the brightest optical giant arcs that are known. One, an arc redshift of 1.7 that we found in 2010 or so, and this sunburst arc, which you may or may not have heard about. It's a more recent discovery, but it's actually the brightest optical giant arc known. So both of these sources were found relatively recently. But if you ever, say, had access to a time machine and wanted to reinvent the order in which we address certain astrophysical topics, you can actually go back to things like the Palomar plate surveys, photographic plate surveys, and find these sources in photographic imaging. So you don't actually need a modern multi-band wide field imaging survey to find some of these amazing sources. Jumps out there pretty obviously. The same thing is true of the sunburst darkness in the south. So I think you'd have to wait until the 70s because there wasn't an all-sky photometric survey or photographic plate survey of the southern sky. It's a little while later, but both of these were before I was born. And so I think it's pretty fun to think that we're finding things that, when I say bright, are really, really exceptionally bright, and that you can do pretty unique things with. So the backbone, well, I should say, why this is being presented at the Gemini conference is because the backbone of a lot of the follow-up data was taken with Gemini. And so a couple of people have already mentioned the powers of nod and shuffle. Jillian in particular talked about how it's a really powerful technique. We've used a lot of Gemini time over the decade plus to perform a lot of follow-up nod and shuffle spectroscopy of these sources because it's a really, really powerful tool and a really efficient tool. These are not super high redshift clusters, kind of typically redshift of a half, but they are very dense in the sky, and they all show multiple of these extended strong lensing features. And those galaxies can be at any redshift, right? We're dealing with potential redshift desert effects here. But it turns out nod and shuffle spectra are really, really effective at targeting tons of these things at once. We can even use modified strategies where some sources get targeted for 100% of the exposure, some for half the exposure. That's what's kind of shown here. If you follow this really faint giant arc, you'll note that there are slits catching it at two different positions. Whereas if you were to look at other, say, bright cluster galaxies here, you notice that only gets a slip half the time. It's a really customizable technique that we've been able to use to really get a great effect. And yeah, so I think that's really all I need to summarize there. A lot of the results have come out in a number of papers, but just to give you a sense of what we're kind of finding, I picked out these figures from, I think this is my 2011 paper, so this is not even old news. But it's cluster cores, all obvious strong lenses. And if you can see the sort of horizontal red hash marks, those are all the things that we measure redshifts for. So it's typically 2 to 3 lens galaxies per field, and typically on the order of 10 cluster members, which is pretty impressive considering that each one of these gets observed for something like an hour and a half. So this was an incredibly powerful follow-up tool that Gemini delivered. And then there's the next slide. There it is. When I kind of preparing for this talk was actually fun. I've never given a talk where I just got to look through like all the old observing programs we had and tally things up. So I was a little surprised at how many programs this was, more than I thought. But this is our Gemini usage to do work with these lensing clusters over the decade and a half. The very first observing program I was a part of as a graduate student is right there in 2007. And then we recently were approved for 2022B. So this is, as I said, spanning pretty much my whole career. But the really cool thing is it's a fair chunk of time, but really, we didn't mean to do like a survey level program, and this isn't really even quite at that level. But I'm really proud to say that we've been quite effective. That even especially for a small team, I was a little surprised, in fact, at particularly how much science this data has produced. So it's been a really great data set to work with. So there's a lot to do with strong lensing clusters, and I try to do as much of it as I can. Broadly, it can be broken down into two things, right? You can use it to study lens background sources. We're using the lensing as a magnifying glass. And then also, it's interesting to study the lenses themselves. Again, I do both of these things. And so the rest of the talk is really just going to be a buffet of some of the exciting stuff that we've done and or would like to do with these sources that were all fed by Gemini data. So focusing first on the lens sources, I'll pick out a really fantastic result. This is a spectacular lens source. We're looking here at Hubble imaging, but the source was characterized using data from a number of programs. Just I'll give shout out here to the fast turnaround program that was actually really essential to characterizing the system on a short time scale. Lots of different ways to get great Gemini data. It's a system that when you correct for the strong lensing, you build a strong lens model, de-lens everything, construct what that lens galaxy looks like in the source plane. This is what you see. The scale bar here, kiloparsec. If you're kind of squinting and holding your fingers up and guessing what sort of structures you're resolving here, the answer is that you're resolving little star-forming clumps of some sort that are down to about 30 parsec scales. And this is a redshift 2.5. So this is right smack in the middle of cosmic noon and probing physical scales of star formation that are pretty exciting. And in fact, if you're a person that wanted to understand the diversity of clumpy star formation in galaxies across cosmic history, you can make a plot like this. All the gray points here are tracing out basically measurements of star-forming structures in the local universe. So obviously we have no trouble resolving things that are nearby. But up at higher redshift, you see all these colored points. There have been a lot of measurements made over the years trying to measure the scale of star formation, how big are clumps. And you'd see these measurements of giant star-forming clouds, which you're really seeing all up here, even up here with a lot of lens systems. But what this source revealed is, in fact, that there is a high redshift population of star-forming clumps that are on the scale of something more like a 30 Doradus or smaller, the kind of stuff that we also see locally. And this is the kind of thing you'd be completely blind to, right? Without one, looking through a large survey to find all the exciting lens systems, and then going through the work of doing the follow-up to characterize them. And just to emphasize that, how much lensing helps you here. This was a series of 3 papers, and this plot is from the third that Heather Jane Rigby led. And this paper started out as just kind of a joke amongst ourselves, and we were like, yeah, sure, let's write a paper. It's really just kind of showing what you would see here if you, what we call, candleified this lens galaxy. So what would it look like if it showed up in the candle's deep fields with Hubble? You can imagine doing the same thing if it were in a similar deep field with James Webb with NIRCam. And in both cases, you're not resolving clumpy star formation in any way that's reflective of what's actually there. And so just to drive the point home again, this is really what the lensing gives you. This is actually an extraordinary system. I mean, it's purely coincidental, right? But if you wanted to, say, start doing spatially resolved spectroscopic studies of these things, it's extraordinarily well matched to the capabilities of what I used to say was an upcoming instrument, but now, of course, exists. So really, really spectacular systems that let you do really spectacular things. And again, this all started with a number of Gemini programs over the years. So this is another great system, one of the highest redshift arcs that you'll find from the ground. So this is basically a G-band dropout, redshift 3.6. It's exceptionally bright. The data, all the data shown here are again that hour-and-a-half discovery Gemini data where we're saying, wow, we'd really like to just measure redshifts of things. This galaxy was so exceptionally bright, and also really in GMOS's sweet spot wavelength-wise, that the discovery spectrum, which is shown here, was actually enough to characterize most of the physical conditions of this galaxy at redshift 3.65. This is pretty high signal to noise. Pretty much every feature you see is real. Some things not marked or intervening absorbers. That's not really science I do or have time to talk about now, but you could do it with these sources as well. And what we were able to do with this thing was identify families of lines Some associated with nebular emission, those are pretty obvious. Others associated with winds from massive stars. Others still associated with multi-phase ISM outflows. And cards on the table. I didn't actually double check that this claim is true as of this year, but it definitely was a few years ago. But this is the best diagnosed starburst galaxy above redshift 3.5, which is to say that we can measure its global properties, we can characterize the properties of hot stars, you can measure really any metallicity diagnostic and the terrestrial and optical you like, and then you can even start doing relative abundances of things like neon, carbon, oxygen, nitrogen, which is pretty incredible. The other cool stuff that we'd like to do with these galaxies or there's plenty of cool stuff, I should say, that's still coming. So we've seen a little bit of James Webb data at the meeting. I figure I might as well show a little bit more. That's because two of these sources that we initially followed up and characterized with Gemini had actually made it into an ERS program we had approved. The idea here was to study two unobscured UV bright star-forming galaxies and then two dusty semi-millimeter star-forming galaxies, all four of which are gravitationally lensed to basically perform spatially resolved diagnostics of star formation, metallicity, ionization parameters, stuff like that. And so, yeah, this program has already taken data, and really it started with Gemini. And a really cool fun fact is that the source, one of the Gemini observed sources from this program was actually the first science target observed by James Webb, which probably was unrelated to the fact that our PI is the project scientist, but I mean, didn't hurt. It was actually purely a schedulability issue. This is an ERS program. It's supposed to be observed early. And if it didn't get observed in June, whenever it was, I think we had to wait like 10 months. And so anyway, yeah, so the EROs happened first, but in terms of targets that technically had the word science attached to them, this was the first, which is pretty cool. And that data looks pretty nice. So this is our near cam and MIRI imaging data of that lens source. As I said, it's a UV bright unobscured star-forming galaxy, and sure enough, when you go into James Webb in the infrared, you don't see a whole lot. Maybe not the most amazing James Webb photo to start with, but it's pretty cool that was first. And again, Gemini is where that started. And so for the last part of the talk here, I'm going to switch gears and talk a little bit more about the galaxy clusters. And this is work that, again, it's a lot of us are involved with within SGAS, and it's really near and dear to my heart. I want to motivate this by saying that a strong lensing sample of galaxy clusters is highly biased, and that's kind of the point. The way that I like to introduce this is to say that, in the cluster cosmology game, often what we're trying to do is connect observations to simulations, and it's always really, really challenging. And so when you typically think of a galaxy cluster sample, SBT, ACT, et cetera, you think of a sample that's selected via some sort of mass observable. You have something that is, scales with mass that you can actually observe, and that's what you count up. And so a mass selection, is emulated here in the simulation results by the sort of purple arrow and shaded region. Now, the simulation result I'm showing here is a plot of mass. So these are simulated clusters in mass, plotted against the strong lensing cross-section of those clusters. So basically, how good of a strong lens is that cluster? This is literally the area at a high redshift source plane within which a galaxy can fall such that it is strong lensed, right? It's literally just an aerial cross-section. And a strong lensing selection is very different from your typical mass selection, right? SPT sample, you just pick all the clusters above some mass, you have some intrinsic scatter, so you don't have a hard line, but that's your sample. Strong lensing is actually much more like this orthogonal selection in this sort of parameter space, right? You're basically saying, well, is there a galaxy cluster lined up with a background galaxy? That's the sort of randomness of strong lensing. And so at some level, it's a random draw, but it's actually a weighted random draw where this is the exact weight, right? And so the reason this is interesting is because if you look at the values here, within constant bins of, say, cluster mass, you see galaxy clusters have cross-sections that span orders of magnitude. So this isn't like a marginal weighting. This is actually quite a strong selection on its own. And it's one that's trivially reproduced in simulations. You can ray trace simulations. We know how gravity works, and you can produce a simulated giant arc sample in the same way that we can go into a survey and find the real giant arcs. And so in some ways, this is an easier selection to connect to simulations. But for my purposes going forward, I think it's just a new and innovative way to try and connect data to simulations. And that's what we have been doing a little of and want to do more of going forward. But just to sort of emphasize the point here of what you could do, sort of what tests can you make and what questions can you answer. In simulations, again, this is a simulation result. you could say, ask questions like, how are the strong lensing clusters biased? And one really easy one to understand is that they're biased in terms of orientation, which is to say that if clusters are triaxial and we are observing them, then the sort of typical cluster population will be randomly oriented on the sky because the universe is pretty random. Strong lensing clusters, on the other hand, will be highly biased in terms of orientation. And that's because if you take a triaxial mass distribution, look at it along this direction, you get a surface mass density that's inflated, right? And that's what produces strong lensing. And so this is the kind of thing we can look for in our observed sample and try to test in simulations. You can also look at things like baryonic cooling physics. Can you condense things down into the core with cooling physics? So this is a simulation with a lot of runaway cooling. This is a simulation with no cooling. And you get very clear signatures in the simulations in terms of what happens when you do one or the other. So the shaded regions here are basically telling you where you'll find giant arcs in these two scenarios. And what this maps to basically is azimuthal coverage, right? If you have no cooling, you get very elliptical things. You get arcs that sort of line up along some major axis. If you have lots of cooling, you get arcs that cover kind of full azimuthal ranges. These are like very relatively simple observables that we can reproduce. And because of Gemini, we have the data to do this. I'm not going to, this is more of a show-off slide. I'm not going to explain all these in detail, don't worry. But these are strong lens models for here, I think it's 37 clusters that Karen Schroen published for us in 2020. Every red curve here is a critical curve. That's a measurement of the surface mass density in the clusters. And all these lens models were characterized by, due entirely to the redshift knowledge that we had from an extensive series of Gemini follow-up programs. That same data allows us to go in and do, weak lensing, strong lensing follow-up of these clusters. These are a bunch of weak lensing plus strong lensing mass profile measurements for, again, a cluster sample. This is from a 2012 paper with Masamune Oguri. You can actually measure masses for these things, out from the virial radius down into the core, just to show that these things do fit quite nicely. The individual measurements are pretty noisy, but if you stack all the clusters together, you get a really, really beautiful measurement. And again, you can perform tests of against simulations. So James G talked about mass concentration. You can measure the mass concentration relation for all clusters, but you can also measure it for strong lensing clusters in simulations because it's easy to find which clusters are strong lenses. So the shaded regions in these plots are the predicted mass concentration relations for strong lensing clusters, and all the red points are the cluster sample I just showed, where you again can directly test these kinds of predictions, and you get results that are reasonably consistent with, arguably slope issues. You can also measure, test the predictions for what shapes galaxy clusters are. So you can take your weak lensing measurements for your strong lensing sample, you can stack them, which has been done here in both just randomly stacking them, taking all the weak lensing maps, putting them on top of each other. Or you can take the strong lensing plus weak lensing measurements from the information you actually have, measure ellipticities of individual clusters, align the weak lensing maps along those ellipticities, and stack them there. That's what's shown here. And if you look kind of closely, you can see there is a very highly elliptical signal here that comes out. This lets you actually measure the ellipticity of your cluster sample, which is something you can directly compare to simulations. Actually, sorry, I think this is the simulation result, and this is the actual measurement. But really, really cool stuff in terms of direct comparisons. And so that's all I have for kind of past results. The last couple slides are just advertisements of where we're going with this. So we had a recent Chandra large program approved to observe the same cluster sample, which, if you've been keeping track, is now a cluster sample where we have strong lensing information, weak lensing information, and now X-ray information. And so this is going to be a great tool for building, sort of extending basically our ability to perform tests of clusters against real data, real clusters, real strong lensing clusters against simulations. The X-ray data are all in, they look great. You can do great stuff with it. Hasn't happened yet, but that's what I'm working on. And then the last thing I have is somewhat of a shameless pitch for what we'd like to do moving forward, which is to fill out our dynamical coverage of these clusters. So we have the Hubble data, we have strong lens models, we have Chandra data, that stuff's been obtained. There's actually a really nice place for us to go back to Gemini and fill in dynamical measurements, both the stellar velocity dispersions of BCGs, so measuring the mass or the gravitational potential on sort of parsec to maybe 10 parsec scales, and then doing cluster velocity dispersion measurements, building up our cluster member numbers. And that's what we're hoping to be doing in the next few years with Gemini. So we've done a lot in the past already, but there's tons more to do. Sorry, I'm a little bit over, but that's all I had. The last slide here was just, once again, advertising all the work that people from my group have been showing off at the meeting. So we have like a half hour left. If you haven't talked to them but thought you might want to, this is your last chance. Please do. And thanks.
Thank you very much for that nice summary talk. We have some time for maybe one or two questions.
No.
I actually had a question related to this spatially resolved measurements of your lensed galaxies. I mean, I guess the work that's been done is doing MOS and getting specific regions. Is what's the benefit of actually spatially resolving it? Can you actually see velocity structure, et cetera?
You mean something like this?
Yeah, something like that. Yeah.
So there's, I mean, a lot of different angles here. So this is no longer cosmology. This is the, star formation, massive stars and star formation and cosmic noon kind of hat that I would have to put on to talk about it. There's a couple of big questions here. One simple question you could ask, which again, I'm not at all a globular cluster person, but you might say, what are these things? Are they globular clusters forming? And so you could imagine going in with near spec, and you can actually can constrain and or measure individual stellar velocity dispersions of these individual clumps, clump by clump within this galaxy. And there's about 35 of them, I think, across the entire structure. So you could actually, with one lensed galaxy here, do a census of 30 parsec scale star forming clumps within a galaxy at redshift 2.5. One of the things that we're really interested in, both here and also with templates, just the James Webb program, is to really address star formation on the physical scales in which it happens. Like, this is a fundamental problem of galaxy surveys. They teach us a lot, right? But in a galaxy survey, the unit is the galaxy. But stars don't form galaxy by galaxy. Stars form giant molecular cloud by giant molecular cloud. And so one of the points of the templates program is to build, literally, maps, effectively data cubes of typical star forming galaxies. On resolved down to the scales that are well below what a field survey can resolve. And so yeah, it's understanding not just how stars form on those scales, but the diversity of star formation, the diversity of, say, ionizing photon production, things like that within galaxies of cosmic noon. So there's a whole thing here that there's no Gemini data involved, but the sunburst arc, this thing that I introduced at the start, is really amazing because it is a Lyman continuum leaking galaxy, but it's not leaking ionizing photons. It's like spewing ionizing photons out. And what we've learned from it is, the galaxy itself is huge on the sky. It's extremely bright in the optical, but the ionizing photons are coming from what is from Hubble essentially an unresolved point source, which is to say that ionizing photon escape is definitely not an isotropic process. It's about punching holes and spewing things out on short timescales. And that's the kind of thing that you simply can't get at in like field surveys, right? You can identify the average Lyman continuum escape from galaxies down to whatever your resolution and limit is in a field survey. But the first lensed galaxy we found that's really producing these things like gangbusters is showing us that if you want to know the physical scales in which ionizing photons escape, you're going to be looking at tens of parsecs. So understanding that process is one of the big motivations here with the lensed galaxies.
Well, thank you very much for that wonderful talk. Let's thank Matthew again.